Good evening and welcome to the Hack AI knowledge sharing session on AI and ML fundamentals. Hack AI is organized in collaboration with the STEM-Up Educational Foundation, UNDP, and SLASCOM to provide opportunities for school and university students to join the national movement that drives social impact. We are inviting innovators across the country to build AI-powered solutions to solve challenges related to selected sustainable development goals. We have a very accomplished speaker to conduct today's knowledge sharing session. If you have any questions, you can send it as a comment on YouTube or Facebook, and we will be happy to answer at the end of the session. Our speaker today, Dr. Varuna De Silva, currently leads the Machine Learning Lab at Loughborough University and is the principal supervisor of one postdoctoral research fellow and 6 Ph.D. students, and the co-supervisor of one Ph.D. student. His team works on engineering application of artificial intelligence, specifically multi-agent reinforcement learning, multimodal computer vision, and simulation models, with a vision to scale state-of-the-art AI algorithms to real-world engineering systems. He is an associate editor of IEEE Access, fellow of the Higher Education Academy in the UK, and a member of BCS and IET. I'd like to invite Dr. Varuna De Silva to conduct today's session.
Thank you, Arifa. Thank you for that introduction. So again, I'm Varuna. I'm a senior lecturer with Loughborough University. So thank you for inviting me to do this session. So I'm teaching most of these topics in AI and machine learning in my school. So for this one, I'm asked to conduct a short session for 40 minutes or so. So I don't know how long I can go with that or how much depth I can go on. But before we start, can I know on the chat, how many of you all have studied machine learning and artificial intelligence? I mean, you can use the chat service on the side, but anyway, let's get moving until people get warmed up with their interaction. So in this short lecture, we are going to look at I will give a brief introduction to the history of AI and data analytics or machine learning, whatever you like to call it, while explaining some jargon associated with these things, because sometimes we use these words interchangeably, and each of these things mean something very specific. We will go on to discuss about fundamentals on how do we train these intelligent agents and what is machine learning. And if we have a little bit of time left, I will also touch upon various aspects of deep learning. So this is going to be on fundamentals, and I'm told there is a mix of students here, those who have a background in machine learning, those who do not have. So I will try to pitch it in the middle. I'm not really sure if I'll do enough justice. So please do give us a shout if things don't make sense, or if I need to go faster or slower. So AI is not a new thing, right? So the concepts of machine intelligence goes a long way back in the history. So it has its modern roots when the mechanical counting machines were built in 17th century. So specifically, the word artificial intelligence and AI as a domain came about, started about with a workshop that happened in Dartmouth College in 1956. So these attendees became the founders and leaders of AI research. So then it went through certain ups and downs, and between 1956 and late 1990s, the domain was heavily influenced by the development of the so-called expert systems. However, the current trends in AI started in late 1990s and early 21st century, where this concept of neural networks combined with the available computational power provided through GPUs, graphical processing units, brought about huge interest on this on the possibilities with artificial intelligence. So for example, a major talking point was AlphaGo, where DeepMind developed this algorithm which beat a professional Go player, and Go happens to be the most difficult board game uh, on Earth. So you can see it came a long way. So it demonstrated in a nice use case, in a confined use case rather, what is possible with data processing, machine learning, artificial intelligence, because it was a combination of a lot of things. So and here in 2021, we are doing a datathon. We are doing a hackathon, processing machine learning, processing with machine learning for sustainability issues. Right? I mean, that is what your hackathon is going to be about. So that's a little bit about history, and I think it is important to make it clear from this moment onwards. So artificial intelligence is any program that can sense, understand what it senses, and make decisions and act on its environment. So it can be any program, it can be any agent. So if you think about a robot, it looks around, uh, understands what goes around, and takes actions in the environment. So if an agent isn't taking action in the environment, or if it is just suggesting possible things, it is not strictly an intelligent agent, right? And then we have machine learning, which is a sub branch of artificial intelligence. Now here, the difference is that in machine learning, we are talking about learning from data. So the more data we have, the algorithms will start improving. Whereas in artificial intelligence, it encompasses everything. So in the previous decades, when we were talking about expert systems, it was mostly about simple intelligence algorithms that people hand coded, people wrote how to act in certain situations and so on. So the difference in machine learning is that now you have the data. Can we learn a lot from data so that your algorithm improves with humongous amounts of data becoming available? So deep learning is a very specific sub-branch of machine learning where you use neural networks. So these are little computational units packed together in millions and millions of them sometimes. And they use huge amounts of data to learn, uh, to reason, or to come up with certain algorithms. So these three are very important for you to understand. So AI algorithms has been there for a long time. So in fact, if you look around for history, so there is an artificial intelligent agent that was done in 980 BC, so around 3,000 years ago. So they talk about a humanoid robot. Uh, this happens to be a mechanical robot during the time of Zhou dynasty. Uh, uh, so, uh, so apparently there was an engineer who built this humanoid robot, and this humanoid robot was able to walk about, make strides. When you touch its cheek, it would start to smile and sing. Likewise. So, funnily, it also goes on to describe that Robot winked his eyes at the king's entourage, and king was really angry. And likewise, so there were even emotional aspects associated with this robot. So it so the robot, the king got angry, and he wanted it to be destroyed immediately. So they had to cut down and understand what was going on. So this is written in historical texts. We don't know how correct it is, how appropriate it is, but there we go. It was there. So this is still an example of artificial intelligence. right? But it was mechanically programmed, but it is not machine learning. It cannot learn more. It cannot learn more from available data. So here let's discuss a little bit about the structure of an intelligent agent. What is an intelligent agent? So artificial intelligence is all about coming up with building these intelligent agents. So intelligent agent is a computer system, is generally situated in a certain environment, in a confined environment. It can sense through sensors, different sensors. It can be video, it can be some kind of textual data. It can be some sensors, and whatever it senses, it needs to understand, perceive, is to understand what is this data about. And then based on its understanding, it is supposed to make decisions. And decisions are when you have several possible actions that you can take in the environment, and you are going to select one of these actions or a sequence of such actions. So that is, these are the decisions that we are talking about. So when it takes actions, the environment changes. The environment in which it is positioned changes. So again, it receives feedback through its sensors. This keeps on going, and this agent lives in this environment. So it always is supposed to achieve a certain objective. But roughly speaking, this is the idea of an intelligent agent. And AI is about creating these intelligent agents. So you can think about several examples. So I think if you all are playing video games, you would have used this kind of intelligent agents. So for example, if you so when you play video games, all the non-player characters in a video game are artificial agents. So these are intelligent agents. The difference is that the actions, the decisions that the non-player characters take in a video game are written by the game programmers. And nowadays you have chatbots assisting with online purchases, for customer services and so on. So this is using natural language processing. Something that is upcoming is driverless cars and certain robots like lawn mowing robots or vacuum cleaning robots. And from the finance domain, we have algorithmic trading. So these are computer algorithms that looks at financial markets, how stocks go up and down, and take a decision whether to invest or not. So it's an intelligent agent to whom we can outsource our investment requirements. So these are simple examples of intelligent agents in the real world. So within the context of artificial intelligence, with respect to those who have worked on this area for a very long time, before the recent advent of deep learning, I think it's right to show you the context of this diagram, where AI consists of creating these intelligent agents. And if you look at the components of this intelligent agent, you can see it can perceive. So there need to be algorithms related to perception. And whatever the data it perceives, it needs to store this information using knowledge representation schemes. So whenever it has to plan for some decision making, it looks into this knowledge representation. It can happen in form of databases. It can happen in form of graphs.
Excuse me, Dr. Varuna. Your
Yeah,
slides aren't visible right now.
really? Oh,
I think you should share screen a bit.
so all this time it wasn't sharing the screen?
No.
Oh, my goodness. That's interesting. Okay.
Because it was the stories, it was very interactive as well, so it's fine. It was very interesting.
Okay, here we go then. Sorry about that. Let me quickly. Yeah, I mean, this is where I was talking to you about the history of artificial intelligence. and about this mechanical robot. Yeah, I was going through this on my desktop. Sorry about that. So this is the architecture of intelligent agent. It sees from sensors, understands what it sees or what it perceives, what it senses. So this is called perception. Based on what it perceives, uh, it makes decisions. So decisions is a sequence of actions, and from a set of actions, what is the best course of actions to take is what decision making is about. And based on this, it takes actions on the environment, and then it receives feedback again, and it keeps on going in this loop. So so we talked about several examples of intelligent agents, video games, chatbots, driverless cars, robots, algorithmic trading. And here I was talking to you about this diagram where you have several components of artificial intelligence identified. So we have the perception attribute, where it is, for example, if you think about computer vision, if some of you are knowledgeable about that, this is about understanding what it sees on cameras and images. Then you have natural language processing, where it's another perception task where it understands text. Then we have knowledge representation. This is about storing this knowledge in form of databases, in forms of graphs, trees, tables, likewise. And then this agent is supposed to reason based on this knowledge available. So it uses certain logical schemes for reasoning and so on. And there are certain other simple reasoning schemes like if-else statements. And based on this, it has to plan to accomplish a certain objective and then executes its plans. So this is the structure of artificial intelligence. Or if you look at a intelligent agent in detail, this is what you will see. But nowadays, when it comes to our discussion and all the talks of machine learning, we are talking only about one aspect of this artificial intelligence, which is learning attribute. So this is about, now, if we can collect loads of data, can we learn from it? Can we improve the reasoning behind this? Can we improve the perception attributes of this, and so on, right? So I will skip this. For example, in autonomous driving, if you look at a driverless car, you have sensing and perception. This is done with several sensors. This is personally one of my research areas. I have several people working on it. That is why I have this in here. So you have sensors like radar, LiDAR, cameras that are suitable to go on a motor vehicle. And based on that, it can understand what is in the environment. These are pedestrians, these are other vehicles, this is a road in which we can move forward likewise. Then it needs to understand based on, in terms of knowledge representation and reasoning, it needs to understand where it is in a given moment of time. So for example, if you know a little bit about localization in robots, that is part of the reasoning part of an intelligent agent. And then based on what it sees and what it understands, it has to take actions. So these actions, these decisions that it has to make is whether to overtake, how to negotiate at a roundabout, likewise. So this is a simple example of an intelligent agent. I'm not going to go through this. I mean, if you look for the NVIDIA driverless car video, you can see some nice example about how deep learning, machine learning is used to train these intelligent agents. So initially, it would not be performing very well. It would have a lot of accidents. But after some training, it learns how to handle these environments very well. So this is an example where you can use data, loads of data over time, and improve your algorithms with machine learning. So this is after it's been trained for some time. Right. So here, to summarize what we discussed so far, we talked about artificial intelligence as the branch of computer science and engineering, which deals with creating intelligent agents, right? And intelligent agents are those who can perceive the environment, plan and execute a certain series of actions to accomplish a certain goal. So now let's go a little bit deep into machine learning. So here we are going to talk a little bit in detail about supervised learning and unsupervised learning, and a few concepts that you may find useful when it comes to building models and creating AI models for real-world applications. Arifa, can they chat on the private chat? Would I be able to see it? Okay, maybe Arifa is not online.
Sorry, doctor. Actually, what happens this is now live on Facebook, YouTube, and Twitter. So if they if they have any questions, they can put it as a comment on any of these platforms. Then you can see it on the comments section of the platform. On your
because okay, on comments. Okay, right. Okay, that's fine. Yeah. Brilliant. Okay, let's move on. So so if I ask you what comes next in this sequence, so here you have x, when x is 1, y is 6, 2 it's 9, 3 it's 12, 4, what is it? So you would quickly be able to tell me that it is 15, right? In class I would actually get you to think about this then and there, but here I can't take feedback. So likewise, what if I ask you what comes next in this sequence? You can take a minute to think about this, but I want you to reflect on what you are actually doing here. So what you're trying to do here is that you're trying to, by looking at the example that is given to you, you are trying to guess what is going underneath, right? So this is the goal of machine learning. Okay, so again, referring to machine learning definition, it is about data, learning from data. The more data you have, the better models that you can build. And the goal of machine learning is about using some past observations, which are also called data points, and trying to explain that with a model. So in coming up with an answer to those questions, you would have thought, okay, this is the model that is underlying here. And based on that model that you have selected, you are trying to predict what comes next. So prediction is a big part of it. Why do you build model? Is to predict. Okay. So it's very important to know what learning is. Here, the learning in a generic term is about estimating the function that is underlying. So based on the data, how do you find a function that best fits this data and best explains this data? So this is the goal of machine learning. So when it comes to machine learning, we have two types of machine learning: supervised learning and unsupervised learning. So since I can't get feedback from you, I will assume there are some people who do not know the difference. Hence, I will go into the next few slides. Otherwise, I was going to skip it. So if you all know about regression and classification, this falls under supervised learning. And in terms of unsupervised learning, we have clustering and density estimation. So density estimation is about understanding the probability distribution of the of a data set. So This is a big part of my research again. So we can use different mechanisms for this, and especially when you do not have loads of data, this is something that we have to work with, because if you can find the underlying distribution, you can still predict, right? But you can still predict with a certain level of uncertainty. So probability as a mechanism, as a language of uncertainty representation is very important when it comes to machine learning. But we are not going to talk much about clustering or density estimation, but rather on the supervised side of things. So if I ask you, how many classes of vehicles do you see here? So this is extremely dumbing down this concept. So what would it be if I ask you how many classes of vehicles do you see in this photo? Now, some people will say there are 2, some people will say there are 3, some people will say there are 20 different classes here. Now, you used your own mechanism to define what are the possible classes. So we are not specifying a very specific criteria as to these are the classes. These are the so you could class them based on the number of wheels. You could cluster them based on the color. You could class them based on the length, likewise. So you can use different criteria to put them into different classes. Now, if we take a different example, now here I'm going to give you a set of examples, and I give you, say, the first row is class 1, second row is class 2, likewise. And if I ask you, which class does this belong to, you will quickly say it is class 3. And if I ask you which class does this belong to, you'll quickly say it belongs to class 1, right? Now, similarly, you are given some data. You are asked which class does this belong to. You'll say you will not be very sure about it, right? This one belongs to class 1. So there's a fundamental difference between this example and this example. The difference is that in this one, we just give you the data. We ask you how many clusters are there, and you use your own criteria, and you say there are 3 classes or 18 classes, 5 classes, likewise. In this one, along with the data, we give it a label. Okay, we give it a label, and we ask you, when you have a new data point, where does this belong to? Then you can easily put them into a specific class. Now, this is simply the difference between supervised learning and unsupervised learning. So in supervised learning, what happens is that along with the data, you have a label given to it. And in unsupervised learning, you have only the data given. And based on some criteria, you process the data. In supervised learning, you use the labels along with the data to come up with models. So let's look at one type of supervised learning algorithms. Apart from regression analysis, you also have classification. Classification happens to be the most popular supervised machine learning algorithm, right? In fact, at some point in the past 2 years, I saw reports saying 90% of machine learning algorithms developed are classification algorithms. So in spite of the time, I'm not going too deep into classification, but I will take regression as a simple example of supervised learning for my discussions. So in regression, regression analysis is about coming up with the relationship between variables. So if you have some data sets and you want to find the relationship between different features of this data set, what we use is regression analysis. Okay, so that's simply what it is. So it is still a supervised mechanism because you will have independent variables and the dependent variables. So dependent variable is always treated as the label in this case. So we have studied this since we were in grade 4, 5, right, plotting graphs. So here we have simple regression analysis and multiple regression analysis. In simple regression analysis, what you have is you are trying to find the relationship between just two variables, whereas in multiple regression, you will have multiple features based on which you are trying to predict an output label. So let's look at this simple example. Now, this is an example where you want to predict the amount of sales based on what a company spent on TV advertisement, radio advertisement, social media advertisement, and newspaper advertisements. So depending on where you spend your money, you want to predict the amount of sales. So for this purpose, what they have done is over a period of time, say over a period of 12 months, they have collected how much money they spent on TV, radio, social media, and newspaper. And then based on that, they want to predict what is the amount of sales. Now, this is a simple example of multiple regression. Now, why do we do this? So for example, if you can come up with a model that relates these different expenditures on sales, you can then try to look at the sensitivity about different features, and then try to determine what is it that drives sales, what is the best proportion of expenditure on each of these channels that we should be spending on. So these are the questions that you can answer. Right. Now, this is an example of supervised learning. Now, I think most of you all are knowledgeable about this, so I'm not going to go into simple details, but I want to rather spend my time on discussing some statistical learning theory concepts relation with taking regression as an example. Now, if we want to try predicting the sales based only on TV ad expenditure, so if we plot the data, this is how it looks like, right? And if we want to predict it with a simple linear regression, linear regression with just a straight line, this is what you will get. Okay, so this is nothing but a y equals mx plus c kind of line. So this is a model that we select. And now, if you can take a bit of time to think about this with relation to a machine learning concept that we discussed. So here, our past observations are our data that we have. Yeah, and we want to predict the amount of sales given a TV ad expenditure. So what we are trying to do is we are trying to explain the relationship between sales and TV ad spend using some model. So here we want to find the best fitting line. So this is the learning process that happens here, function estimation. And in doing so, what we are going to do is we are going to try out various different lines, various different parameters for m and c in this y equals mx plus c model to find the best fitting line. So this is about function estimation. And once you have fitted this line, you can forget about all the data, and then you can use only this model to predict the amount of sales if you asked, what would be the amount of sales given a certain TV ad expenditure. Now, think about this model for a moment, and I want you to think, is this the best fitting line? Can we go for a more complex model? Now, this is a typical problem that you will encounter when you are trying to fit models onto data. So why don't we go for a third order polynomial? Why don't we go for a more complex model? Wouldn't this fit well onto the data? It fits better, perhaps, right? Now, there's a caveat here, in the sense You can keep on opting for more complex models. However, you need to have a lot of data to try out more complex models. Because if you look at the difference, in this example and in this example, we are still fitting a third order polynomial. For example, in here, we have only 10 data points. In this one, you have around 100 data points. As you can see, the model that you are coming up with is very different. Now, if you all know this, if you all have studied this, this is called overfitting. Okay, this is called overfitting. Overfitting is when you're trying to fit a model, you're trying to estimate a function, and you don't have lots of data. What happens is that if your model is very complex, it will start fitting into the noise in this data. It will try to fit onto the fine details in this data, and that is overfitting. Okay. Whereas if you have loads of data, you do not have that issue that much, and you can go for a more complex model. With this, I also want to refer to a concept called inductive bias. Now, as you can see, in this particular example, you looked at the data and you determined, okay, let's fit a straight line. Or then you thought there is a bit of a knee-jerk kind of reaction at the very beginning of this data set. So let's try to fit a third order polynomial. Okay. So you're looking at the data and you're selecting a certain model. Now, there is a concept in statistical learning theory, which is called inductive bias, is that, the learning method you're selecting will favor certain decision rules over the others. Okay. So what it means is, if you are selecting a straight line, for example, you will only be limited to certain decision rules. And if you're selecting a third order polynomial, you will always be limited to a different set of decision rules. So each learning method you use is good at only dealing with certain decision rules. Now, here is a nice dilemma, is that you cannot build a completely unbiased system. Okay. So whatever the model you're selecting to fit onto a data set will be biased. Okay. So this is called inductive bias. So you are selecting a method, if it is a straight line fitting, if it is a polynomial fitting, or if it is, in the case of classification, if you're going to stick with support vector machines, as compared to logistic regression, or as compared to random forests or decision trees. Each of these methods are good, right? But remember, each of these methods are capable of only certain decision rules, in the sense it can predict only a certain types of functions. So in theory, what happens is that what you can achieve with a given type of model on a given set of data is pretty limited. Okay. And then there's something that goes very much closer with this concept, is something called no free lunch theorem. Okay. So here the concept is that you cannot there is no method, there is no machine learning method that is the best for all problems across all data sets. Okay. So people need to try out different models for a data set. They have to work with different data sets, with different models, sorry, and then select an appropriate model. So that is why, if you think about it, there are various types of classification algorithms. There are various types of regression algorithms, right? And people need to come up with more and more, because each of these models will fit into different underlying distribution types. So one thing that is good in one data set will not be good in another data set. Okay, so this is called the no free lunch theorem. So these are concepts that you need to keep in mind when you're trying to fit models onto data. Another thing that you need to keep in mind is what is called the bias variance trade-off. Okay, now this is similar to the concept I was touching upon in the previous slides about fitting a straight line or a third order polynomial in the case of regression. So you have to select the model with the right complexity. You cannot select a very simple model. You cannot select a very, very high complexity model. Both are not good. When you select a very low complexity model for a given data set, and if it is not appropriate for that underlying distribution, we call it a high bias setting. That is what you see in this slide here. And on the other hand, if you select a very high complex data set, a very high complex model for a given data set, what happens is that that model will overfit onto your data. Okay. So on one side, you have a high bias setting where it will underfit onto the data. It cannot capture the underlying variations, underlying distributions. On the other side, you have a system, a model that overfits onto the data because it is capturing noise. So you have to balance these two things. So finding the right fit is what we are saying as trying to do the bias variance trade-off. Okay. So how do you do this? If you all know about this, and if you don't know, please go and read about this. It's called cross-validation. Okay. So this is a simple technique that those who are doing data science would know very well, but those who do not know don't do this, right? So if you want to find the right model that fits onto the data with inductive bias in mind or no free lunch theorem in mind, or on the other side, if you want to find the right complexity for a given data set, we have to do cross-validation. So here the concept is if you have 1,000 data points, you will have to break it down into training set and a testing set and leave the testing side completely aside. Okay, do not touch upon that until the very end of your project. And your training set, you can break it down into training and validation set. So you can do whatever you like in terms of model selection, finding the right model or finding the right complexity and all those things using this data set. And there are different methods of doing cross-validation, right? Like n-fold cross-validation or leave out kind of set cross-validation. So you can read a little bit about this thing. So this will help you to build a model with the right complexity, with the right and selecting the right model, while making sure it also generalizes well to unseen data. And that is why you leave out a test set at the very beginning. When you leave out a test set, what happens is you can treat that as unseen data. Right? So whatever is left, which is used for training and validation, is seen data by the model development process. Okay? So when you're presenting your results in terms of your accuracy or some kind of a loss function or something, for the outside world, what they require to know is what is the performance on the testing set. Then there are some other concerns related to selecting the testing set, like the balance of the set, balance of the data and all that, but I'm not going to go into that detail, but you can read more about it. Another concept from statistical learning theory that you need to be aware of is the so-called curse of dimensionality. Right. So in most often when you get data sets, you will have many features embedded in this. You will have many features and maybe a label associated with this data set. Right. Now, a common problem that you face when you're trying to fit data is that what features should we use? If you have loads of features, should we use all of that to come up with the right model? Now, the answer in short is no, right? Because you are affected by what is called the curse of dimensionality. Dimensionality is the number of features you have or number of features you use to build a model. Now, the irony is this: the more features you use, the better your model performance will be on the training set. But what you do not know is that when you use more features, your model overfits onto your data, overfits onto the noises in your data set. What happens is that it performs very bad on the test set. So this is called curse of dimensionality. So you have to make sure that you select only as much as possible features, or only the important features for your activity. Okay, so don't use all the features in a data set and you say you build the best model. It may not fit well onto the test set. So so for example, so there's a fine point at which your model performance will be good both on the training set as well as on the test set. So with that, I think what I want to summarize in this particular short lecture is that, so selecting the right features you need to be aware of. Okay, so in the data set, just because you have loads of features, don't use everything. And then selecting the right model complexity is another important thing, right? And I didn't touch upon this, I touched upon this a little bit as well, is that if you're going to fit complex models, if you're going to select things like deep learning or random forests, remember you need to have loads of data, okay? Because there is no point in using a very complex model, to fit onto a small data set. Yeah. So if you have loads of data, then it can fit very well onto a neural network. If you don't have that, it is not very good enough. Okay, so that's the part where I can end this lecture on. Or can I ask Prabhat, Arifa, can I go further, or because I have more to speak if I want to, or shall we call it a day with this and take some questions?
So far, Doctor, we don't have any questions. There is only one response for your previous question on how many vehicle types you can see.
Yeah.
What was the answer there? No question.
What was the answer then?
I can see 3. One of
okay, very good. So somebody gave it some thought rather than just saying
watching. Yeah. Yeah, other than that, there's no question, but we can always invite our viewers to put their comments, feedback, questions on any of the social media channels you are on right now. So Dr. Varuna can answer them. Otherwise, Doctor, we can proceed. Like we have enough time.
Okay, give me a rough time. How long can I go for? Because I can go for 10 hours if you want to. I have my lectures.
Yeah, I think the original schedule was till 6, I guess. But yeah, let's even we can even go for another 1 hour, Doctor, if you are.
Okay. What I will do is I will go through a few more slides and we will end it there and probably take some answers there. Yeah. But it would be nice, sure. Those who are attending, if you can put some questions in, we can discuss about it. Otherwise, it may not be appropriate to go on and on. Right. So now let's, since we have a few more time, let's look at a few examples of training. How do you train intelligent agents? Okay. So in the previous short set of slides, we discussed about supervised learning and how do you select the right model, what you have to keep in mind and all that, and how it relates to concepts in statistical learning theory. So I started this lecture by saying most of machine learning falls under supervised learning, unsupervised learning. Something I didn't say is that there is also a concept called semi-supervised learning. Okay, so here the concept is that there are different methods of semi-supervised learning. One very popular method is called reinforcement learning. Okay, and then there are other methods like active learning, where you get human in the loop to provide some feedback, to give labels to some data, but you have a data set where you don't have labels in general. You prompt the human to provide some labels. Now that is called active learning. So here we are going to talk about training intelligent agents and a specific concept called reinforcement learning and imitation learning, which falls generally under the category of semi-supervised learning. So we started this discussion by saying the fundamental goal of AI is to train intelligent agents who can act autonomously in an environment. So if it is not acting autonomously in an environment, it is not artificially intelligent agent. Okay, so it's important to keep that in mind. So whenever people talk about AI, they are almost always talking about some aspect of machine learning or some aspect of deep learning. So this is something for you to keep in mind. So where do you have these intelligent agents? So we had a small example of algorithmic trading, natural language processing, as in chatbots or driverless cars and all that. But traditionally, in the domains of social sciences, we have this concept of agent-based models. Now here, the nice thing is if you want to simulate a social system, which might be suitable when it comes to your sustainability-related projects that you have in mind, is that you can build a set of intelligent agents and multiply them. You just have to replicate them and put them together and see how they behave, how they interact with each other, and how what emerges out of that. It's a form of using intelligent agent, a simple description of agents, and then putting huge amounts of them together to see what is emerging. So so a typical example is when if you want to model how to evacuate a fire in a certain building, and how do you build an environment where people can evacuate safely as soon as possible. You have to simulate different situations. Where can the doors be? Where can the exits be? And likewise. So for that, you can use agent-based models. Another slightly different domain, which is very popular in the domain of computer science, is called multi-agent systems. Now here the situation is that you define a big system as part of multiple small elements, where each agent in this case is a software component, software algorithm that can interact with different components. A good example I can give you is if you take a flight, airplane, the entire system of wings, how the engines work and the flaps work, landing gear work, all these things, along with the decisions the pilot makes and all that, everything is coupled as a multi-agent system, right? Now, typically what happened is that it is the computer scientist who define how these individual agents work. The difference between multi-agent systems and agent-based models are that in multi-agent systems, you will have almost always multiple heterogeneous software components, whereas in agent-based models, you will have many of simple but similar agents put together. In agent-based models, what happens is that when they start interacting, the phenomena that emerges is what is important. What we don't know is what happens when agents are put together and they interact in certain ways. Now, these are two domains in which building intelligent agents was popular in the domain of AI, right? Now, coming into the recent times of AI and machine learning, reinforcement learning is a very popular technique that is used to develop these intelligent agents who can learn from trial and error. Now, what is reinforcement learning? It is very similar to the way we train pets. Okay, so if we want to train a dog to obey to our commands, what do? We would ask it to say, for example, if we want it to learn to sit down. When we ask it to sit down, what we do is we will ask it to sit down, and whenever it sits down, we would give it a small treat, and whenever it wouldn't do that, we wouldn't give it a treat. And what happens after a period of time you doing this is that the dog learns to sit down even without receiving a treat. So this is all what reinforcement learning is about. You have an objective. You let the agent trial and error. In this case, dog is going to trial and error. As the environment, we are going to give it some treats. We are not going to tell it. We can't. There's no way for us to communicate with this dog. So we are going to just give it a treat, just to signify this is what we wanted to do, right? And we have defined a reward function in such a way that it will guess and it will start doing what we want it to do. So this is a typical way of training intelligent agents to take intelligent actions. Now, this is the trial and error based method, okay? So what happens after some time is this dog learns to sit down even when we don't give it a treat. So you would have experienced reinforcement learning, for example, when you are playing video games. For the first time when you are given a video game, you wouldn't know what to do with it, right? You would just be playing around with the commands. After some time, you start to figure out little bits and pieces of this game. Okay, this is how I'm going to get more marks. This is how I'm going to lose my lives, likewise. So what happens is after some time you playing this, you come to know how to progress from one stage to another stage, right? So this again is a typical example of how we are accustomed to learn from reinforcement, from positive reinforcement. So this is the concept that is called reinforcement learning, and it is used to train robots. For example, if you have a robot dog here who we want to go and pick a ball, we would just define a reward function, and whenever it does what it wants to do, or whenever it takes a sequence of actions which makes it closer to the goal, it would be receiving good rewards. What happens is over a period of time, it can learn to act intelligently or learn to accomplish the task that we want it to achieve. So not all problems can be framed as a reinforcement learning problem, because some problems we need to define. We will find it difficult to define reward function. Okay, so for example, let's take the example of football. Okay, so if you want an agent, if you want to develop a robot that can play football, it's very difficult to define the reward of this agent, because we can't say always try to hit a goal, because that is not how the game goes, right? You have to pass, you have to take shots, and likewise you have different things that you have to do. So for in situations like this, what is most common, and this is my particular branch of research activity, we do something called imitation learning. Now, imitation learning is another way we humans learn. Now, here the idea is that we learn from observing what other humans do or other experts do. Now, this is used a lot in the past, for example, in the robotics domain, where you demonstrate how to accomplish a particular task, and the robot's idea is to accomplish this using the observations. So the key to this is that you have to select, you have to get some data about good demonstrations, and from these demonstrations we can learn what is the best decision-making policy. The decision-making policy is the sequence of actions that you have to take given an observation. Yeah? So this is used in football. So for example, if you want to build a artificial model of footballers, what you can do is you can use the data, how the footballers moved on field over seasons of play, and what happened to the ball, where was the ball. So using these player movements and the ball movements over a long period of time, we can learn how, if we were to replace one of these players with an artificial robot, what is the decision making of this robot going to be like. Yeah. So now the objective of this kind of activity is not to build robots that goes and plays football, but rather, if you want to measure how good a particular player performed on field, right? How would you measure this performance? How would you measure the decision making of a player on court? So for that, what we can do is we can compare it with the computational benchmark. Now, the computational benchmark is the intelligent agent we learned using the data. So this is the idea. Okay, so you can think of similar applications if necessary. So, and then we have multi-agent policy learning. Especially in this case of football, you will not have just one agent like a robot trying to open a door or trying to spill beans onto a cup. But in the case of football, you will have multiple intelligent agents. So, for example, you have the offending side and you have the offensive side and you have the defensive side, right? Here, the idea is that these players have to cooperate with their own team members, but compete with the other side. So the idea is that you not only have to take actions as a single agent, but you have to take actions as a group of agents. So you have many examples of this, like in game intelligence, where you're trying to train automatically train intelligent agents as non-player characters in video games. Right now, the non-player characters are usually defined by game programmers. But what if we can define intelligent agents that can learn from playing the games? So what would happen is we could come up with some unique gaming experiences, novel gaming experiences, which can benefit from this. So for example, Microsoft Research, for them, this is a big part of their activity in building intelligent agents. So right, I think with that, let's stop our discussion. So we also talked about two techniques, reinforcement learning and imitation learning. Now these are two semi-supervised machine learning techniques. The idea is that you can train an intelligent agent to take a sequence of actions that lead up to a goal, as compared to supervised learning and unsupervised learning, where our objective is to look at a data set and to predict something. But here it's about taking actions in an environment. So yeah, I think with that we'll stop our discussion and we'll take any questions we have. Thank you very much. Rabat, Arifa, do we have any questions?
Questions, you can drop in your questions using the comment section on either YouTube or Facebook. We have a question here. It says, to start developing machine learning models, is there a minimum number of data that we need in a data set?
No, not really. You can build a model with one data point, right? And that is that will be the task for the brilliant data scientist. If you have loads of data, anybody can build a model, right? So if you have little data, how do you build models? That is when you will start to innovate. You will start to bring about your deep knowledge in data science. So if you have little amounts of data, always think about building probabilistic models, right? So the moment you have one data point, you can build a model, right? However, the uncertainty of this model will be extremely high. you have 2 data points, the uncertainty will be a little less. So you can keep on building that. So this is where if you want to study this area, that is where you should be studying, or you should be putting your effort in, right? Yeah, you can build models with one data point.
Another question is, what is the best accuracy percentage so that we can avoid overfitting and so the model is acceptable?
There is no such accuracy percentage we can give it like that. So I will show you another slide if I can find here. Is that you need to what you do is you break it down. You have your training set and your validation set. Okay, you fit the model onto your training set. You look at how is it performing, and you do this at different levels of complexity. And every time you train a model on your training set, you measure how well it does on your training set, on your validation set, for example. So let me show you a small slide. You can see this, right?
Yes, can see.
So what happens is here in this case it is a regression problem I have at hand, but you will have a similar thing in terms of accuracy, but on the other side of the curve, right? But here the point is that you have a training set and you have the validation set. Okay, so here if our objective is to find the right complexity for our, that fits well onto our data set, but it also generalizes to the unseen data set. The point is that you can't touch the unseen data set, which is a testing data set, until you finish your model building process. So you use your training set, you break it down into training and validation set. And what you do is you train the model on the training set, and you use the validation set to see how well it does on the validation set. So what you will see is, for example, in this case, we are trying to fit a regression model, and we are measuring the root mean squared error as an error metric. So as and when you increase the complexity of the data set, in terms of, as and when you increase the complexity of the model that you're trying to fit, which is the polynomial degree, you will see it starts to do increasingly well on the training set. But what happens on the validation set is that it will start to come down. The error will start to come down, but after some time it will start to increase again. And this is a common behavior we noticed. Okay, so here you have a pattern where it starts to fit well onto the training set. On the validation set, it starts to fit well, and after some time it doesn't do well. It doesn't do well because it is overfitting. After this point, it starts to overfit. That is why it doesn't do well on the validation set. So this way you can find the good level of complexity. So in this case, I could select anything between 3 and 7, for example. Okay, I would rather select something like 4 or 5, but this is how you do it. Yeah. I hope I answered your question properly.
Thank you, Dr. That was a really good explanation. It seems that we don't have any other questions. Thank you, Dr. Varuna De Silva, for a very educational session. And just before we wind up, it's still not too late to register your solutions for Hack AI 2021, and you have till December 21st to submit your solutions. And if your solution is selected as a finalist for Hack AI, you will get the opportunity to be mentored by domain experts, and the winners will be awarded cash prizes. Also, thank you everyone for joining today. Have a good weekend.
Thank you very much.